8th semester mechanical engineering students. For all those who are logging in for the first time, let me just brief you with the online class schedule that we are following. This is going to be a 1-hour session with each half consisting of a 20-minute lecture followed by a 10-minute question-answer section. You can post your doubts or queries in the Q&A option that is available in your screen. Do post your doubts and queries in the question-answer Q&A section. Today, we have with us a very eminent faculty, Dr. Jobin Varghese, Associate Professor, Department of Mechanical Engineering, Adi Shankara Institute of Engineering and Technology. Dr. Jobin Varghese has done his graduation and post-graduation from Anna University, Chennai, and got his PhD from NIT Calicut. And he has over 5 years of experience in teaching as well. He also has a number of papers to his journals and publication list, along with a number of conferences and seminars that he has done. It is a great pleasure to have you, sir, to handle a session for our students. On behalf of SAP, I welcome you, sir, to the session. Over to you, sir.
Thank you. So I hope I have just shared my PPT and it's visible to everyone. Okay, today, I hope it's audible, right?
Yes, sir. Yes, sir. It's audible.
Okay, thank you. So here I would like to go on with the bevel gears, and last time we have gone with, in fact, helical gears. And when we compare this one, the design is almost same in this. Or there are little differences here. So I'll just show you this one before that we'll go into theory. And this time, I'm not going deep into theory, rather I just going deep into the design work that is important for the students to learn better. Okay, well, these are the contents where I would like to just do. That is the bevel gear theory. The annotation. So this is like bevel gear theory, then the bevel gear design procedure, bevel gear demonstration problems. So these are 3 areas where I'm going to cover. And okay, so there are different type of bevel gear sets like straight bevel gear, spiral bevel gear, zero bevel gear, meter bevel gear, hyper bevel gears. However, we are just focusing only on the straight bevel gears since that covers in our syllabus. So the result will be going only with the straight bevel gears, and the spiral bevel gears having more importance when comparing the practical applications, and zero bevel gear. Meter bevel gear has different applications in different areas where we are not covering the design of these things in the class. So first come to the bevel gearing. So major thing when compared to the helical gearing, you can see the pitch circle itself, that is a surrounding circle itself is different. In the case of helical gear, you can see that was a circular one. However, this has a cone frustrum. So in fact, this can be well clear here. That is when you extend this one towards the center, this becomes a cone. Also, you can see this is a cone. So there are 2 things like pinion and gear. And in fact, there is one more important factor is that we cannot combine a bevel gear with a spur gear or a helical gear or a worm gear. So bevel gearing should have the pinion and gear in both in the same shape, or it should have the same module and the same pitch circle like this way. So it's a conical surface, you can see I can extend towards the apex. And In this case also, this is actually the spiral case where I told that I will not be covering right now. That is majorly two teeth profiles are there, that is straight as well as the spiral one. And the other all divisions are based on the axis which is kept over this one. So this one is the one case. There are many models of the cases we can make over this one, like the bevel gear can be kept here so that when the axis is drawn, it is perpendicular to the axis of the gear, so that you're having a 90 degree. In this case, in fact, the pinion is kept somewhere offset to the center. Since it was the center, and this is the center of this one, this pinion is kept somewhere offset. And when it comes to the case, usually we'll be using the bevel gear to connect at 90 degrees. That is when we are to transfer the power from one form here to the other one at 90 degrees, we will be just connecting the bevel gear. However, that is not only case which we can deal with, where the bevel gear can be changed into different ways. That thus comes the different types of gears like meter gear, the other type of gears are coming into scene here. So you can see that it's not 90 degree, in fact. So it is it's an obtuse angle greater than 90 degree. Also, this is greater than 90 degree where it comes. But when we draw the axis together, what I'm saying is the surfaces are greater than 90. When you draw the axis together, when we compare the axis, in fact, it's an acute angle that is 60 degree. Axes are meeting here. So axes are meeting here at 60 degree. Then here we can see that when we see the axis together, it comes to 120 degree. However, outside peripheral looks like it's an acute degree, but however, when you take the axis, it's not acute. In fact, it's an obtuse one. So what happens is that it can rotate clockwise. This rotates anti-clockwise. That is normally that's in the gears. When one rotates in clockwise direction, other will be rotating in the anti-clockwise direction. So that is the bevel gear rotation. And usually major application we can see this one in the differential of the vehicle, especially in the big vehicles or multi-utility vehicles or even lorries. So we can see that there are bevel gears that are arranged. The reason is the major reason is that the power from the engine will be coming to one point, and that should be distributed to two wheels. That's what you can see here. That is the power, the shaft comes to this one from the engine, then it is distributed to two wheels. So there is a 90 degree division of the power or supply of the power is there. So as a result, this is mostly used in differential in case of this one. And then there are greater technology, many technologies here. Haven't included much technology over there. However, we can have some technologies seen here, bevel gear terminology, that is because of the axis of the rotation, that the axis, how the angle is there with this one. So already I have just shown to you how the axis is between the 90 degree axis over this one. And once you come to like, this is like removing all the teeth over the surface, this comes the pitch surface, where when we see the pitch surface, we will exactly see what the shape of that particular gear. In the case of spur gear as well as the helical gear, the shape is a cylinder. However, in the case of bevel gear, it's a cone. So there are two possibilities here, like we can extend this one. This is from the pitch circular line can be extended here also to here to create an apex. Also, we can extend two lines in this direction as well. Like we can just do in this direction. So in this direction, this one you can see here, that is along the pitch surface, we are drawing a line here. Also, pitch surface, we are drawing a line here. So this, in fact, this comes to a point called the cone, that is the apex. And now the pitch angle is calculated as, that is the angle between the horizontal surface and the inclined surface. Now again, pitch angle varies, depends upon the configuration, how this is kept. As in fact, this is the case only when that is in 90 degrees. We are arranging in the 90 degrees. This shows like it will be drawing over this one, and there is an axis. This is the axis along with we are drawing one. So that is a case of pitch angle here. Now, so 90 degree there is shaft, and this decrease changes and the configuration changes to different name. That is in here happens about the pitch angle. Now, this is somewhat the theory and where I had to go with the design. So I'm not going into far into theory. So, do we have any questions just before we get into the design?
So no one has posted any questions as of now.
Okay.
But there's a request that you can use a little bit of Malayalam as well, in between. That's what a request came in like that.
Okay. Okay, so maybe I have to use some Malayalam. So should I repeat this one? Or I mean, should I repeat the same theory in Malayalam?
No, sir. In your in sessions, I mean,
Okay.
When you continue, you can use Malayalam.
Okay. Okay, we come into the design part here. So design of bevel gears. So major things were, I think these things you can understand just by reading from this. The Malayalam conversation is not required at all in this case, right? So there are two design procedure of the bevel gears. Bevel gears into design procedure ne pattiyana njan parayunnathu. Like material selection, that is the first case in any design. If you take any case of any designs, the material selection is the first step. And in case of bevel gear in the case, let's select suitable material if not given from the table 12.7 page 234. So ഇവിടെ ഞാൻ ഉപയോഗിക്കുന്നത് മഹാദേവന്റെ ഡാറ്റ ബുക്കാണ്. കാരണം എന്താ വെച്ചാൽ അത് കൂടുതൽ കുട്ടികളും കൂടുതൽ പ്രിഫർ ചെയ്യുന്ന ഒരു ബുക്കാണ്, ഷോർട്ട് ബുക്കാണ്. സോ ഐ യൂസ് ദിസ് വൺ ഫോർ കാൽക്കുലേറ്റിംഗ് ദിസ് വൺ. നമുക്ക് ഏത് ബുക്ക് ഉപയോഗിക്കാം, PST ഉപയോഗിക്കാം, ഇറ്റ് ഡസന്റ് മാറ്റർ. ഹവർ നമ്മൾ കംഫർട്ടബിൾ ആയിരിക്കണം അത് ഉപയോഗിക്കുന്നത്. എന്നാൽ മാത്രമേ ഇത് ഈ സബ്ജക്ട്സ് ചെയ്യണമെങ്കിൽ we should be well aware about the data book and we should be flow into the data book to find all the values. Otherwise it's difficult to solve the problems in the design. So first one is material design. So first we will go to 12.7 page 234 and I will demonstrate it when we get into the problems. Then second is identifying weaker part. So നമ്മളെപ്പോഴും ഞാൻ കഴിഞ്ഞ ക്ലാസ്സിലും പറഞ്ഞിരുന്നു, ലൈക്ക് വീക്കർ പാർട്ടിനാണ് നമ്മൾ ഡിസൈൻ ചെയ്യുന്നത്. കാരണം സ്ട്രോങ്ങർ പാർട്ടിനെ ഡിസൈൻ ചെയ്താൽ വീക്കർ പാർട്ട് ഒരു പക്ഷേ ഫെയിലായി പോകാം. അങ്ങനെ സംഭവിച്ചു കഴിഞ്ഞാൽ ആ ഡിസൈൻ ടോട്ടലി കൊളാപ്സ് ആവും. സോ വി ഓൾവേസ് ഡിസൈൻ ഫോർ ദ വീക്കർ. സോ ദ കണ്ടീഷൻസ് വി യൂസ് ഹിയർ ഈസ് ദാറ്റ് if the material used for both pinion and gear is same, then the pinion is weaker. അതായത് ഒരേ മെറ്റീരിയൽ ആണ് യൂസ്. അപ്പോൾ ക്വസ്റ്റ്യൻ്റെ ഉള്ളിൽ മെറ്റീരിയൽ തന്നിട്ടില്ല എങ്കിൽ വി അസ്യൂം ദാറ്റ് we are using the same material for that one. ആ കേസിൽ പിനിയൻ ആണ് വീക്കർ ആയിട്ട് നമ്മൾ എടുക്കുക. ഗിയറും പിനിയൻ ഓൾവേസ് വീക്കർ ബിക്കോസ് അത് സ്മോൾ ഇൻ ഡയാമീറ്റർ തിക്നെസ്സിൽ കുറവായിരിക്കും. അതുകൊണ്ട് ഒബ്വിയസ്ലി ദാറ്റ് ഈസ് എ വീക്കർ വൺ. ബട്ട് if the material used for both pinion and gear are different, suppose pinion gear is used steel, the other one we are using some mild cast iron or something. So one is stainless steel and cast iron something. രണ്ട് ഡിഫറെന്റ് ആയിട്ട് നമ്മൾ എടുക്കുക. അല്ലെങ്കിൽ ക്വസ്റ്റിന് തന്നിട്ടുണ്ടെങ്കിൽ then the strength factor സിഗ്മ ഡി മൾട്ടിപ്ലൈഡ് വൈ എന്ന് പറഞ്ഞാൽ വൈ ഇസ് ദ ലൂയിസ് ഫാക്ടർ, ഫോം ഫാക്ടർ. അത് വെച്ച് മൾട്ടിപ്ലൈ ചെയ്തിട്ടുള്ളത് എടുക്കും. ജസ്റ്റ് വി ക്യാൻ ഡെമോൺസ്ട്രേറ്റ് ദാറ്റ് ഇൻ ദ ക്വസ്റ്റ്യൻ. നൗ വൺസ് വി ഫൈൻഡ് ദ വീക്ക്, the design is totally based on the weaker part. So first is determination of how to design and what should be considered for the design. The step 2 module calculation. Module calculate ചെയ്യണം. ഞാൻ പറയുന്നത് എന്തിനാ module calculate ചെയ്യുന്നത്? നമ്മളെപ്പോഴും ഗിയർ എടുക്കുന്നത് എന്തിനാന്ന് വെച്ചാൽ we have to mesh it together to make some gear trains or to transfer the power from one form to other form or from one axis to the other axis. So ആ കേസിൽ എന്താ ചെയ്യണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ മൊഡ്യൂൾ കാൽക്കുലേഷൻ ഇല്ല എങ്കിൽ, മൊഡ്യൂൾ അറിഞ്ഞിട്ടില്ല എങ്കിൽ നമുക്ക് അടുത്ത ഗിയർ ചൂസ് ചെയ്യാൻ കഴിയില്ല. അപ്പൊ അങ്ങനെയാണെങ്കിൽ മെഷ് ചെയ്യത്തില്ല, ഒരിക്കലും പവർ ട്രാൻസ്ഫർ ചെയ്യാൻ കഴിയില്ല. So that we should find the module calculation. Design the second part എന്ന് പറഞ്ഞാൽ we have to go for module calculation in case of gears. So if two cases ആണ് ഇവിടെ വരുന്നത് വെച്ചാൽ, ഒന്ന് if diameter is known, അതായത് ഡയമീറ്റർ നമുക്ക് തന്നിട്ടുണ്ട്. ഡയമീറ്റർ എന്ന് പറയുമ്പോൾ ഡയമീറ്റർ ഓഫ് എ ഗിയർ എന്ന് എപ്പോഴും പറയുമ്പോൾ we always use the pitch circle diameter. So pitch circle diameter അറിയാമെങ്കിൽ we'll use the question we'll be using this one, m is equal to ft by this equation that you can see from 12.37 page 280. So ഇതിൽ FT എവിടുന്ന് you can use this equation, and this everything we will see in the problems. Next comes the diameter is unknown. The case diameter is known and diameter is, I hope I have written second time. So diameter is unknown. Diameter unknown എന്ന കേസിൽ നമ്മൾ ചെയ്യേണ്ട ഒരു പ്രോബ്ലം എന്ന് വെച്ചാൽ we have to take the module equation, this one. അപ്പം we come to this one. I just have a small have to come to this point. About there is a confusion with the velocity in the last class, so I have to make clear this one velocity. That is, velocity is given by pi d and by 60. അതെങ്ങനെ വരുന്നു എന്ന് വെച്ചാൽ നമ്മളെന്ന് വെച്ചാൽ 2 pi r, ഒരു സർക്കിൾ എടുത്താൽ സർക്കുലർ സെക്ഷൻ ആണെങ്കിൽ 2 pi r, we will take always 2 pi r, which is the distance. That is 2 pi r means pi d multiplied by how many rotations, എത്ര പ്രാവശ്യം റൊട്ടേറ്റ് ചെയ്തു. അപ്പൊ ടോട്ടൽ ഡിസ്റ്റൻസ്, ഈ സർക്കുലർ സർക്കംഫറൻസിലുള്ള ടോട്ടൽ ഡിസ്റ്റൻസ് കിട്ടും 2 pi r into n times ടോട്ടൽ ഡിസ്റ്റൻസ് കിട്ടും. അപ്പൊ നമുക്കറിയാം ഡിസ്റ്റൻസ് വെലോസിറ്റി ഈക്വൽ ടു ഡിസ്റ്റൻസ് ബൈ ടൈം. അപ്പൊ നമുക്ക് തരുന്നത് RPM എന്നാണ്, റൊട്ടേഷൻസ് പെർ മിനിറ്റ്. ഒരു മിനിറ്റിൽ ഉണ്ടാവുന്ന ടോട്ടൽ റൊട്ടേഷൻസ് എത്രയാണ്. അപ്പൊ നമ്മൾ ഒരു ഒറ്റ റൊട്ടേഷൻ ഉള്ളത് 2 pi r അല്ലെങ്കിൽ pi d എന്ന് കണ്ടുപിടിച്ചു. We are taken as 2 pi r. We are taken as 2 pi r pi d, then multiplied by number of rotations. So pi d n divided by RPM ലാ തന്നത് കൊണ്ട് അതിനെ എന്ത് ചെയ്യാന്ന് വെച്ചാൽ നമ്മൾ സെക്കൻഡിലോട്ട് മാറ്റണം. നമുക്ക് മീറ്റർ പെർ സെക്കൻഡിലോട്ടാണ് ഇതിന്റെ പിച്ച് ലൈൻ വെലോസിറ്റി ആണ് നമ്മൾ കണ്ടുപിടിക്കുന്നത്. സോ അതിനെ ഇതേ കാണുമ്പോൾ by 60, കാരണം മിനിറ്റിനെ നമ്മൾ ഓട്ടോമാറ്റിക്കലി സെക്കൻഡ്സിൽ മാറ്റിയാണ്. സോ by 60 അങ്ങനെ ചെയ്ത് കഴിയുമ്പോൾ നമുക്ക് എന്ന് വെച്ചാൽ മീറ്റർ പെർ സെക്കൻഡിൽ കിട്ടും. അപ്പൊ രണ്ട് കണ്ടീഷൻസ് ആണ്. ഇപ്പൊ d എന്ന് പറഞ്ഞത് മീറ്ററിൽ തന്നിട്ടുണ്ടെങ്കിൽ നമുക്ക് ഈ ഇക്വേഷൻ ഉപയോഗിച്ചാൽ മതി. അല്ല, d എന്ന് പറയുന്നത് മീറ്ററിലല്ല മില്ലിമീറ്ററിലാണ് തന്നിരിക്കുന്നതെങ്കിൽ by 1000 കൊടുക്കണം. പക്ഷെ അങ്ങനെ കണ്ടീഷൻ എന്താ വെച്ചാൽ n എന്ന് പറയുന്ന RPS-ലായിരിക്കും ഉപയോഗിക്കുന്നത്. Then V is equal to pi dn by 60 into 10,000. ഇതിന്റെ കേസിലെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമുക്ക് എന്താ വെച്ചാൽ മില്ലിമീറ്ററിലും RPM-ലും തന്നിരിക്കുന്ന കേസിലാണ് നമ്മൾ ഇക്വേഷൻ ഉപയോഗിക്കുന്നത്. സോ ഡിപ്പെൻഡ് അപ്പോൺ ദ ക്വസ്റ്റ്യൻ യു ഹാവ് ടു യൂസ് ദിസ് വൺ. ദിസ് should not be a confusion furthermore anymore. So in the case of once the diameter, we have to use the module here. Then check for the sigma d in both cases. There is static stress. നമുക്കൊരു പെർമിസിബിൾ സ്ട്രെസ് തന്നിട്ടുണ്ടാവും. ആ പെർമിസിബിൾ സ്ട്രെസ്സുമായിട്ട് നമ്മൾ എപ്പോഴും എന്താ വെച്ചാൽ ചെക്ക് ചെയ്യണം. ആ പെർമിസിബിൾ സ്ട്രെസ്സിന് മുകളിൽ ഇത് പോയിട്ടുണ്ടോ മൊഡ്യൂൾ കാൽക്കുലേറ്റ് ചെയ്തതിന് ശേഷം. അപ്പോൾ each and every time we will be using this one, that is using the equation sigma d equal to ft by equation. എന്നിട്ട് നമ്മൾ ചെക്ക് ചെയ്യുക സിഗ്മ ഡി ഗ്രേറ്റർ ദാൻ പെർമിസിബിൾ വാല്യൂ. പെർമിസിബിൾ തന്നിരിക്കുന്ന വാല്യൂവിനേക്കാളും ഗ്രേറ്റർ ആണോ സിഗ്മ ഡി എന്ന് നോക്കുക. അങ്ങനെയാണെങ്കിൽ നമ്മുടെ ഡിസൈൻ ഫെയിൽ ആവുകയാണെങ്കിൽ വി ഹാവ് ടു അഗെയിൻ റീകമ്പ്യൂട്ട് ദ മൊഡ്യൂൾ ആൻഡ് റീസ്റ്റാർട്ട് ദ പ്രോസസ്. അല്ല എന്നുണ്ടെങ്കിൽ ഇഫ് സിഗ്മ ഡി കാൽക്കുലേറ്റഡ് സ്റ്റാറ്റിക് സ്ട്രെസ് is less than permissible stress, then we can continue. Then finally calculate the phase width. Phase width equation ഉണ്ട്, അത് വെച്ച് കാൽക്കുലേറ്റ് ചെയ്യാം. Then come to the dynamic load calculation. That is the next step. Dynamic load calculation എടുക്കുന്നത് എന്തിനാന്ന് വെച്ചാൽ gear is always running. It's not a static case, it's a dynamic case. So dynamic force should be given. ഇതുവരെ നമ്മൾ ചെയ്തതെന്ന് വെച്ചാൽ what you have done is we have just depend on the Lewis equation, Lewis method to design. Now we go to the Buckingham methods. Buckingham methods എന്തിനാന്ന് വെച്ചാൽ എപ്പോഴും dynamic load calculate ചെയ്യണം. So we start from static ending in the Buckingham's method. So calculate the dynamic load using the equation for the Bevel Gears. I am getting many questions, so what I was suggesting is like you can just ask at the end. Okay, I'm just going into the design. So finally, endurance limit calculation. Endurance limit calculation എന്താണെന്ന് വെച്ചാൽ എത്ര നേരം വേണമെങ്കിലും എത്ര സമയത്തിന് ശേഷമാണ് നമ്മൾക്കത് എന്താണെന്ന് വെച്ചാൽ എത്ര കാലങ്ങൾക്ക് ഉപയോഗിക്കാം. മേ ബി ഫോർ ഇയേഴ്സ് ഓർ മേ ബി ഇൻ എമൗണ്ട് ഓഫ് hours, days, എത്ര കാലം ഉപയോഗിക്കുന്ന എൻഡുറൻസ് ലിമിറ്റ് നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്യും. ഫൈനലി വെയർ ലോഡ് കാൽക്കുലേഷൻ. ദാറ്റ് ഈസ് മിനിമം വെയിറ്റ് നമ്മൾ അതിൽ കൊടുത്തു കഴിഞ്ഞാൽ വെയർ ഉണ്ടാവില്ല. സോ വെയർ മീൻസ് റബ്ബിംഗ്, ഫ്രിക്ഷൻ. അപ്പോൾ ഫ്രിക്ഷൻ വെയർ, ആ ഒരു ടീത്ത് വെയർ ആയി പോയി കഴിഞ്ഞാൽ then we have to change the gear. So what is the safest load that we can apply so that the wear does not occur? So that is FW. This is the equation. Now we have to find out the value of K and find the suitable material for gear and pinion using table 12.16, page 239. So, okay, Somebody asking F endurance is less than FD. So F endurance is less than FD. We have to take the calculations further. We have to repeat it. So that we'll just solve everything in the problem where you will get better understanding. So demonstrative problem, that is the diameter unknown, pinion and gear. So unknown diameters for pinion and gear. Okay. So can you hear me? Any problem with that? Hello?
No, sir, you can continue. So, can I interrupt for a second here?
Yeah, sure.
I request all the attendees to please post your questions in the Q&A option that is available on your screen. You can use the Q&A option to post your questions. We'll be addressing your questions at the end of the first session. Okay, thank you.
Okay, so let's continue. Here, so I told, like, when I say the design procedure, there will be many questions over there, but when we solve a problem, in fact, that our questions can be sorted out here. So this is a question like design of a pair of bevel gears to connect two shafts at 60 degree. ഇതാണ് പറഞ്ഞ 60 ഡിഗ്രിയിൽ കണക്ട് ചെയ്യാന്ന് പറഞ്ഞ two shaftsന്റെ ആക്സിസ് തമ്മിലുള്ളത് 60 degree. That is not 90 degree. That is less than, in fact, 90 degree. That is acute angle ഇത് കണക്ട് ചെയ്യാം. കണക്ട് ചെയ്യാന്ന് വെച്ചാൽ it will be I have already shown in the theory how it does the connection. Then the power transmitted is, നമുക്ക് ഡാറ്റ മാത്രമാണ് ആവശ്യം വരുന്നത്. Power transmitted is 25 kilowatt. Power is equal to 25. ഞാൻ ഇവിടെ എഴുതിയിട്ടുണ്ട്. So P is equal to 25 kilowatt RPM. N1 is equal to 900 RPM. So we have taken RPM of the pinion as N1. Then gear ratio, reduction ratio, that is gear ratio is equal to 5:1. Then there is a angle that is 20 degree full depth involute angle. So this is the pressure angle which is given as 20 degree full depth involute. Then pinion gear, that is equal to 24 teeth, and it's asking to design. So what is, check the design for dynamic and wear consideration. നമ്മൾ പറഞ്ഞ dynamic എന്ന് വെച്ചാൽ FD as well as FW. ആ കണ്ടീഷൻസിൽ നമ്മൾ ഇത് ചെക്ക് ചെയ്യുക. അതാണ് ഗിയറിന്റെ ഡിസൈൻ എന്ന് പറയുന്നത്. So this is the initial stage what we are trying to do. This is always the normal stage. നമുക്ക് ഈ പാരാമീറ്റേഴ്സ് എപ്പോഴും അറിഞ്ഞിരിക്കണം. That is N1, N2, Z2, Z1. ഈ പാരാമീറ്റേഴ്സ് നമുക്ക് എപ്പോഴും അറിഞ്ഞിരിക്കണം എല്ലാ ഗിയർ ഡിസൈൻ പ്രോബ്ലംസ്. So അതിന് ഏതെങ്കിലും ഒരു പാരാമീറ്റർ തന്നിട്ടുണ്ടാവും. ഇവിടെ given it as I. So the relation here is I equal to N1 by N2 is equal to D2 by D1 equal to Z2 by Z1, or I is equal to Z2 by Z1 because already we have got one variable, that is Z1 is already given here, that is Z1. So we can find Z2 as I is known, 5:1. So the further calculations moves in this case. So step by step, I'm just 5 is equal to, that is I is equal to Z2 by Z1, where Z1 is already given, then multiplied by, you will get what is Z2. First part is this should know the number of and N1 that can be used at the stage, or you can calculate in the afterward stage. That doesn't matter. That depends upon our thoughts. So first, some material properties. So in this question, you can see no materials is specified here. The power transmitter is no material is specified. As a result, we can assume the material. So since material is not specified, let us assume that both pinion and gear are made of same material. So same material, in fact, we will go to select a particular material from the table, and I'll just show you, like, we can go to the table, which I have referred already there. It's, you can see table 12.7, page 234, which I have appended here. This one is got to force steel about 0.3% C heat treated. Usually, if not given, you can choose anyone. However, usually we are using a forged method for the gears to have a better strength. Then further, moving on this one, once the material is selected, next we have to find out the weaker gear. So that is a pinion or gear, which one is like. So usually we will be using the method called as strength factor method, that is sigma T multiplied by the Lewis factor Y. Since both pinion and the gear made of same material, the pinion is weaker. This was the condition already we have already dealt with. That is, pinion is taken as the weaker one since the material is same. That is sigma d1 y1 less than sigma d2 y2. That is the condition we are using. That is, this is sigma d1 y1 is the that for the pinion, the strength factor for the pinion, and this for the gear. So in fact, we say this is weak. Now come to next part is that one. Next, our idea is to find out a virtual number of teeth. So as like in the helical gear, there is also a formative gear we are making here. Okay, formative gear we are making here. That is, so power equations all will come in as follows. So virtual number of teeth is equal to Z by cos delta. In this one, we have to calculate what is delta. That is the first thing. For calculating what is delta, and we can see this equation here. The Z is equal to in 12.35D, page number 218. You can see Z equal to the equation is shown here. So you can use that equation. Then for the once we get the equation, we have to find out the delta, and how to find the delta on the same page itself. Not on the same page, on the other side, like 215, page number 215, 12.29. You can see tan delta 1, tan delta 2, these equations, that is equal to sine theta by, and finally we are making sine theta by I plus cos theta. So using this equation, it is calculated. I plus cos theta, we are calculating what is delta 1 and delta 2. So in fact, that are the angles of the pinion as well as the gear. Now using this, we are finding what is virtual number of teeth for each pinion as well as gear. That is, we will calculate for pinion and gear. So you can see that is virtual number of teeth for pinion is equal to, we are substituting delta 1 here, delta 1 here. Okay, so comments are coming over there. Okay, so 24 by cos 8.95. This will be equal to Z2 equal to Z1 by cos delta 1, that is equal to, you'll get two values here. Once the virtual number of teeth is calculated, so the first idea is to calculate the module. We are moving towards calculating the module. So these are the pre-calculations already done to make you better understand. Okay. So first, this is the module calculation. You can see, go to the data book, you can see the equation here, the module calculation, Ft is equal to, using this one. Now, however, you can see there is a difference. This is 18 MT sigma D CV YZ into square root of Z1 square plus Z2. In fact, this equation is not given in the data book, and I have shown how this equation is obtained. So this is available in the data book. That is 12.37, page 280. Now there are some diameters is unknown. We have B equal to L by 3, L by L minus B equal to 3 by 2. And Ft, all the equations you can get and substitute, and finally we will get the equation. So hope that we have to by heart this equation, that is m equal to square root of n, because many parameters are included in this which is non-parameters, and maybe we cannot solve with this equation, so that we are just moving to this equation by incorporating all the parameters inside this one, and finally we will get the equation like this. And next one is we have to substitute the values in this one. So we are calculating the power here. That is okay. Power is equal to equation we are taking from 2 pi nt by 60. I hope this is available there in the shaft section also. P equal to 2 pi nt by 60, where 2 pi n into t is given as mt. So 25 p is equal to 25 into 10 power 3. 2 pi into n is taken as 900 into mt by. From there we will calculate. I'm not calculating step by step, however, just showing you idea. It is a demonstrative problem to just show you how to do that. From this we have to calculate mt, because the reason is that one module has a variable called module has a variable called mt. You can see that module has a variable called mt. So we are calculating this mt here. You can see the mt here. MT is calculated. Then there is another factor with that we have to calculate is CV. So assume that CV equal to 0.5. So if not given, and if there is no way to find out this one, we can assume it as 0.5. And then there is a form factor called y equal to pi y1. y equal to pi y1. This already we have seen the helix also. So that is not mapped correctly. So there is an equation that is y equal to pi y1, which is the equation is correct, but the mapping is not right. So 12.24b in the page number 214. From there, we can choose an equation pi into 0.154, and finally we will get what is the value for y. So we'll get the value for y as 0.368. We can substitute this here. Then the other factors is sigma t, z, and z1 square plus z2 square. Now, since all the values which the others is given, that is 220 sigma t is a static stress already given, the permissible stress, and C, like we have calculated the CV as or assume the CV as 0.5 and Y is calculated. Then the number of teeth, that is number of teeth we are calculating for the module, because we are just taking the pinion as the weaker one. We are designing the pinion. So we are taking the pinion, and this is the sum of the squares of both the pinion and the gear. And finally, we are finding the module. So once this is the first step we have completed with this one. Now we have to standardize this module 3.43 in the table here. We can see near to 3.53, that is we have taken the 4. That is already 3.43 is the, then there will be a question that why can't you go for 3.5? It doesn't matter, we can go for that. However, we are just taking some module that is very near to the which is a whole number, which is easy to manufacture as well. So we'll take this one, and finally we come to this one as a module. Then finally we calculate the pitch circle diameter of the pinion. Since the module is get here, there is an equation here that's d equal to m into z. From this equation, you can calculate what is pitch circle diameter of the pinion, that equal to m into z1. And once you got pitch circle of the gear, you can, there is an equation d2 by d1 I equal to d2 by d1 or d2. We can calculate this one. I hope all may be aware of this type of calculations.
Sir, can I interrupt?
Yeah, sure.
There are a few questions in this session, I guess. Someone has asked, why is CV taken as 0.5? Why is it assumed as 0.5? And
Yeah, can I answer that?
Yeah, please, sir.
Yeah, in fact, CV, we have an equation to find out the CV with the velocity. We have to take the velocity, and finally we have to calculate the CV. However, just for our assumption, like to make it quite simpler, we have taken the 0.5. That is like, or else we can calculate the velocity if the RPM is known. Then if the RPM is known, obviously we can calculate that one CV from the equation from the data book.
Okay, sir. And some Abhijit has asked, how is MT calculated?
MT. Yeah, that is, I think there is a problem with showing here. That is P equal to 2 pi NT by, so usually just write some words. So I hope I can see that P equal to so this is, there is a method to find out this one. That is, we can find out. So here this torque usually will be taking us MT. In this case, we'll be taking us MT, where we usually use this NT as the normal equation and the wide applicable equations. So from this we can find T. Since the power is already given in the question, and N is also given for this one, so we can calculate the T. Hope it is clear.
Okay, sir. A boy has asked, can we select any material from the table? I guess it's applicable in the beginning. Can we select any material from the table?
Yeah, I understood. Like we can select, but however, the forged one gears will be better in the case, and it's when it's heat treated, it had to transfer large power. So that should be hard enough. As well as the forged method gives more power into that. That's why we are taken. Doesn't matter. We don't have to select any other. If you select any other, and finally we will be coming to the material, the correct material after designing, and we will find out the best material. Maybe the assumed material may not be correct at the end of the design. So we'll come to the conclusion that we should take this material. That's not a matter.
Okay, sir, one more question. How could we choose whether it's involute or sub-teeth system if the details are not given?
So involute system, in fact, the bevel gear, we are following a involute teeth. So they will be giving the involute teeth as per the syllabus. It's covered as the involute teeth, and I don't think that they will be giving the profile is always involute. Or even though there will be a difference in the pressure angle, it doesn't matter. We can use that data to calculate or design. I hope that the student might have meant.
Okay, sir, you may continue. We'll go on to the questions later on.
Okay, so once we calculate the module, this is the step which we are moving. The module is calculated, and finally from the pitch circle diameter is calculated. Now, so once the module calculation is ended, we have to go with the face width. Obviously, there is a cone distance that is I show you when it come into being, and the next one is since the procedure is standard, we have to calculate the face width. So how to calculate the face width is we have to choose L by 3. So in this equation, you can go into the data book to page number 280, 12.36. B is less than or equal to L by 3. That is, the face width should be less than or equal to L by 3. So that is the condition. So for us just to calculate this one, we have to take L is equal to half into. So for this we need the L. So L is equal to half into D1 square plus D2 square. So you can see here L is equal to half into D1 square root of D1 square plus D2 square, or there are other equations as well, but we have taken this equation here, and from this we have to calculate L. So L is equal to D1 plus D2, that is the circle diameters which already we have done here, that is 100, 500. These are the pitch circle diameters of the gear, and you are just substituting that one to get the L. Once we get the L, B equal to L by 3. So face width also calculate. That's also almost a factor to be found out under the module. So once it's completed, next part is to check for sigma D1. That is static permissible stress. We have to check. We have to check the permissible stress. That is sigma D equal to FT. And this equation we can find out 12.37 page 218. So that is this is the equation here, and remember that the equation is given as like this way. This is the equation given in this one. However, sigma D, we have to extract the sigma D from this. We have to extract the sigma D as equal to FT divided by. Okay, we have to calculate that one. We have to take care of that one. Sigma D direct equations are not given. From this, we are calculating sigma D. Now, next comes is that we are checking for sigma t, and where this velocity we can calculate velocity. As somebody were asking why CV is taken as, it doesn't matter. You can go into a data book and take the CV by calculating the velocity, since all the velocity is calculated here. Okay, so in this case, pi d1 n1 by 60. So that I made clear when I tell the design. So how the parameters are given, depend upon that one, we have to calculate the V. If it is RPS, N is given in RPS, then we should not take, we should not consider the 60. If in RPM, then we should consider the 60. And D1 is in millimeter, then we should divide by 1000. If in meter, we should not divide by 1000. So all the things are taken. So final value is equal to, that is meter per second. Now, Now there again 4 generated teeth, that is this the which we have assumed somewhere here, that is 0.5, and we are just making sure whether this comes into the right way. So CV equal to 6.1 by 6.1 plus V, and finally we get that as 0.5642. So if not, you are not taking 0.5 nearby, so almost the assumption is similar. If you are not taking also, that will be corrected in the way when we check sigma D. So when we are checking the sigma D to understand whether our design is safe until this one. It should be under permissible stress. If you have taken 1.53 or something, then finally when you check sigma D will be always greater than the calculator. Sigma D always will be greater than the permissible stress. So that can be avoided. That we will show into while we going there. So then FT, for FT we are calculator for the equations, and you can get the equation from this. Okay, I will show you. And I had hyperlinked it here, so you can go to 12.8a. You can go to 12.8a, page 206, to find out the equation ft equal to 2mt by t1, and you can calculate the ft. Once all is given, we can go to find the sigma d, which is already I have shown this, and the values, substitute all the values in this one, and we will get the values as 1134 megapascal, which is less than 220 megapascal. Suppose in some questions, if they are not given this sigma d, where you can even find out from the data book in the first design module 1, we have found out how we are finding the material static strength of this one. So that is permissible strength. You can find out this one. So once we find this into being, sigma d can be calculated to 20 megapascal and is less than another, design is safe. So you can go further. This calculator, well, okay. Then comes to the face width B. So we have to make sure that B should be correct as we are drawn, so that B equal to 85 mm. So we fix it that L by 3. We have used the equation L by 3 to find the B. Then comes to the dynamic tooth load. So last class I haven't solved up to this. From this here, I just stopped with here. This time I thought I can include this one also. So dynamic tooth load is equal to, this is the equation where you can find that equation from data book. FD is equal to, so you can see FD is equal to, I have not marked here. So anyhow, we can see that FD is equal to, this is the equation. You can use it. So once the equation is used, now K3, you have to take K3, the value is given under this in page 207, under 12.12, the K3 value is given. So you have to substitute the K3 here. Now for calculating this one, first we have to find out the error 1. So that should be calculated for this one, and show you that the factor called C. C has to be calculated, and we have a small procedure here to calculate the factor C in this one. So first we are taking 4 meter per second as a velocity. Already we have calculated pitch line velocity ago. We got 4 point something, so we are rounded it to 4 meter per second. Now corresponding error we are calculating from the table here. So once comes to 4 meter per second, the corresponding error is 0.0710. So this is like this is maximum allowable or permissible error in action. So between gears, this error is allowed, where we can add the error in the case of bevel gear. So you can see this that is equal to 4 meter per second. Error is taken here from this table. Now second case is that we have taken the 20 degree. 20 degree as the involute, like a pressure angle that is equal to 20 degree we have taken, and steel combination already we have chosen the material as steel combination. Now we have to find out the 20 degree steel combination and error equal to 0.6 from this table. Again, I think the table is not mapped here. So here there is an error that is 0.06 millimeter, that is equal to 60. From that you can find out what is the value of C. Now we have to calculate actually the value corresponding to 0.0710, not with this one. So this is how you will be thinking how you get the 0.06. In fact, like we have taken the nearest value to 0.07 from this table, that is table 12.12 page 236. We have taken the value, and corresponding value under this C is given for alpha equal to 20 steel combination. So we are using that one method here, and finally we are calculating the error. So error is calculated by first a ratio of errors, that is 0.0710 divided by, this is another error from this table, 0.06 multiplied by the factor 686.7 for the error that is approximate to this one. So we will get a value that is equal to 812.160 C value. So once we get 812.60, we can substitute C value in this here as well here. Then all of the values we have already calculated, and from this we can find out what is FD. So this is actually, this FD is equal to, that is equal to dynamic tooth load. What I am saying, when it's motion, there is some dynamic force acting on, that is this one. Then it comes to the endurance. To calculate the endurance, endurance is how long it will work without failure. So in fact, F endurance equal to sigma endurance BYM. So this is we can obtain from the data book here, that is page number 219, equation number 12.39, that is equal to F endurance. And this equation, just using this equation, we are taking for alpha is equal to 20 degrees steel combination of BH1, BH2, 200. Again, to go to another table, you can see that 200, 200, that is BHN is equal to 200, 200. Taken as, this how we are taken is like, we are just seeing the 20 degree angle. We are seeing into 20 degree angle here. So that is a absolute, that is a pressure angle, and we have to see that endurance limit 480.5. These are the values based on which we'll take. I'll show you one more time. So you can see here, K, we have taken this one BHP steel combination having BH1 and 1 equal to BHN2 equal to 200. That is equal to K value, and the total value of that one equal to 480.5 megapascal. Now F endurance we can find out by that is we are taking sigma endurance, so that you might have seen from here. 480.5, that is for 200, 200, we have taken 200, 200 steel material, that is BHN, and based on that one 20 involute. This one, this is in fact we are taking this one as the material. However, this may not be the material, it will not exist. Later it will change. For this one, we can see endurance limit is given as 480.5, and this is 20 degree. And with this data, and with the data of the K, we are calculating the F endurance, total F endurance. And finally, we are getting F endurance value as this one. Now, again, we are checking whether the F endurance value is greater than FD. Checking F endurance value is greater than FD. So what happens that the material is safe against static tooth load. So static load, F endurance should be greater than FD or not. Then it will be the safe condition. So what is the here is like you can see F endurance equal to 39.84. That is greater than FD dynamic load, which is calculated, that is equal to 24.87. So the material is safe against the static tooth load. Now to find the BHN number, that is the hardness number, the gear can withstand any wear or erosion or some forces into that one. We have to again find out this one, that is from the equation FW equal to this equation you can use, and here to note like there is a ratio factor QE that will be soon we will be using. So again, we'll be calculating the ratio factor since the ratio factor.
Excuse me, sir.
Yeah, sure.
Sir, we've got 5 more minutes.
Yeah.
We'll have to wind up in 5 minutes.
Yeah.
And I've got 1 or 2 questions related to the topic that you've taught right now.
Okay.
Why is BHN taken as 200 and 200? That's a question someone has asked.
Okay. So, like I told you, like this is an assumption which we have taken, and this BHN may not be always correct. And the final, we again choosing the BHN that we are correcting the BHN at the final stage. Initially, we are taking assume that the same material, and we are taken 200 as the BHN minimum to be used, and that will be corrected at the end of this. Once we come to, you can see that finally we are changing the BHN to different values. Yeah.
Okay, sir. You can finish your session.
Yeah. So like that way we have to calculate the ratio factor, and finally we find that the where, and again we are checking this condition, that is where force is greater than or equal to Ft, and you can see that finally that is the equation here, d1bq by the equation is greater than 24.87, and finally we found out that is k is greater than or equal to 1.62, and again this you like for the value k greater than 1.6, you will get the value that is equal to 1.746. So that's the design of the bevel gears. And this is the case when I told you diameters is unknown. And when the diameters is known, similar the equations will be changing and you'll be taking. So I hope at the time I'm just stopping this one. There was a diameter known, and there is no difference here. Only change I have to just show you is that we have to see the strength factor. We have to determine this weak pinion based on the strength factor. You can see here. We'll take the strength factor, and which is lesser. We always take that one to decide. We have to find the pinion based on the strength factor. So here you can see sigma T2 into Y2 is less design. So when we take this one, this is the less one. We assume this as the gear, or we have taken this as the gear. So we will now the design will be based on gear, on the weaker gear, not on the pinion. So with that, I'm just stopping the session. So,
okay, sir. Let's just answer 1 or 2 more questions. Abiran has a question from the last session. He says, while calculating FT, the CS value is unknown. Where can we find it? That's a question he has asked from the last session.
Yeah, CS value, it's also we are just calculating from table. I calculate the CS from where I mentioned the CS.
So in the last class, he is saying, not this class. In the last class session.
I have to go through the data book one more time to find out. That's on the bevel gears. So is there any other question by that time I can just find?
Yes, sir. Yeah, meanwhile, there is another question. Mahadevan and PhD, is there any change in procedure of doing the design? Or is there any, or there be any change in weightage of awarding marks? That's a question.
No, in fact, there is no change in awarding. But however, the reason is that they have used a different parameters. So when somebody is teaching in with the other data book, and when you change the data book, the parameters they have taken will be different. So helix angle can be delta, can be changed to other psi or something can be. I have seen in different texts, different conventions they are used. That is only the way there's a difference I have seen. And mark weightage will never come, but only thing that you have to just mention which data book you have been used there. That's all.
Okay. And there is a question. If it is given to take steel as a material, can we take any steel like cast steel, stainless steel, etc.?
Yeah, sure. That you can take. It doesn't matter. But the design, final stage, I told you the concept of the design is always we are making the gear that is less than the permissible stress. That is a major factor here. Okay, so whenever we will be checking the sigma d continuously, even after every designing this one. So what happens is that മലയാളത്തിൽ പറയുകയാണെന്ന് വെച്ചാൽ എന്താണേലും ഈ നമുക്ക് തന്നിരിക്കുന്ന പെർമിസിബിൾ സ്ട്രെസ്സിൽ താഴെ ആയിരിക്കണം നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്തിരിക്കുന്ന സ്ട്രെസ്. അതാണ് എപ്പോഴും ചെക്ക് ചെയ്തുകൊണ്ടിരിക്കുന്നത്. അങ്ങനെ ചെയ്യുന്ന ഡിസൈൻ എപ്പോഴും ശരിയായിരിക്കും. അതാണ് കണ്ടീഷൻ പറഞ്ഞിട്ടുള്ളത്.
Okay, sir. So shall we wind up?
Yeah, wind up. Yeah, and something called a CS. I have to find it out. Or maybe in the next sessions, or I can just
we'll address it during the next session.
Yeah.
Okay, so thank you, sir, for your valuable time.